Okay.
Yeah?
So first off, hi everybody. My name is Dourmashkin. I'm at MIT, and I just would like to thank you for coming today. And I hope I can make your time worthwhile. I should apologize first because wait, let me see. Can you hear me like this?
No, but better if you have a microphone.
Better with the microphone. And also, if I speak rapidly, I'll need to slow down. And I just apologize for not speaking Italian. I've been here a few times, it's kind of really need to learn more Italian. So, as I understand the program today, there's two different aspects. The first part is to talk about teaching in the classroom, pedagogy, and about active learning. And the second part is to tell you in the afternoon a little bit about the TEAL project and the history of it and what we're doing at MIT. So this morning I thought we'd launch into just how we teach in the class and the things we do. So the problem is I'm a physicist. And how many people here are teaching in the sciences?
Materie scientifico-tecniche.
And languages. Languages. Because I think there's something very natural about teaching both languages where students need to practice all the time and they can't learn a language without practicing. And I think ultimately it's the same idea about science. That it's not something that one learns through just passive listening, but it should be actively practiced on a regular basis. The same way if you wanted to, what I think is most important is to think, how do we learn about language? We practice, we talk with each other. How do we learn about, if you want to learn how to play a musical instrument, you don't watch somebody. It's nice, but you'll never learn how to play an instrument without watching somebody. You need to practice, 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 practice again. And the same thing about other things. If you want to learn how to cook, if you want, if you're talking with your friends, so the emphasis here is in our TEAL classroom. It's about interactive learning, about students learning how to discuss, in particular, learning how to practice science, because that's something that students don't naturally do. They do know how to practice sports. They may know how to practice other things like music, but what we want to teach them is how to engage in the learning process with scientific education and learning to talk with their peers. So I thought what I'd do is tell you a little bit how we try to bring that out in the classroom. The echo? It has an echo? Yeah. This is better? A little better? So, I thought I'd show you a picture of Cambridge right now. We have 9 feet, 3 meters of snow in the last 3 weeks, and it just snows like every day. So it was a little challenge. This is my front yard. The snow is piled really high. So what I thought I'd begin with, oh, by the way, I want to thank Christina for inviting me to come. This is the second time I've been to this incredible city month, so it's special for me. Now let's see what's going on here. Okay, so again, I think what I want to do in the afternoon, we're going to talk about our TEAL project. But what we've been doing very briefly is we've been teaching in this active learning format for about 14 years. Our classroom is what I would call second generation TEAL. We copied a model from North Carolina State University by Bob Buechner. But we adapted that model for MIT, and I'll tell you a little bit about how we adapted it later. Other universities in the United States at RPI had started this studio physics, it was called. And I think the word studio, atelier, is really important because the idea is a place to practice. Now, our classroom is primitive compared to this one. It's nothing like this classroom. This is a beautiful space. We don't have, because we're second generation, I would even say this is fourth generation now. So each time you change things, you have more, especially the ability for students to communicate with each other through computers to the board. We don't have that. So the things I say, we have to think about how to adapt it. In fact, everything I say today, it's very important to realize that we designed our program for our MIT culture, our student culture, our faculty culture, our administrative cultures. And because our program is designed specifically for MIT, we had to make lots of decisions how things played out. And so what I tell you today is by no means you should copy these things. They're just points of transformation, ideas to think about. Can they be adapted to your schools? That's the important point. Because everything we did, we made hundreds and hundreds of adaptations to our teachers, how they like to teach. So everything is always figuring out the local culture and how to adapt new teaching techniques into that local culture. So I think it's very important to take the things I say with that idea in mind. I want to take us through a few. So there's many, many types of active learning. The things that I want to talk about today are something that came from Eric Mazur at Harvard called peer instruction and concept tests. And that's why you have these clickers in front of you. Can I ask the teachers a quick question? How many of you have used clicker-type devices in your classroom? Okay, so this will be fun. But you'll see, this is by far the most successful thing we do. And it came from Eric Mazur at Harvard. And I'll talk about that in detail. In our space, MIT is about problem solving, learning how to solve problems. And having board space like you have here, all the whiteboard space, is perfect. And I'll show you some examples of problem solving. Maybe we'll even engage in it a little bit, even though everybody's not a physicist here. But I just want to, we'll pretend you're students, and then I'll show you how we go about it. So it's not necessarily about teaching physics, but about just using physics as an example to illustrate active learning. There are discovery activities where instead of telling students beforehand, this is what you're going to do, they discover ideas, important physical principles, and we'll play around with some of that. I think learning to talk about science is crucial, so discussion questions are very important. And an interactive classroom with tables, students can discuss, and we can talk a little bit about that. Finally, one of our important adaptations was simulations and visualizations. I think in the afternoon I'll talk more about, have any of you used the FETs from the University of Colorado? These are fantastic simulations. They're translated into Italian, and they have English at the same time, so they serve this bilingual need, which I think is fantastic. And they're designed for the high school levels. They come with many, many lesson plans, and they're designed by a research group by Carl Wyman, research group at the University of Colorado. Carl was actually an MIT undergraduate, and he's been a leader in physics education research in the United States, along with Eric Mazur. Carl always says the only reason people listen to him about education is he won the Nobel Prize in physics, which helped in what's called Bose-Einstein condensate. So he's not only a specialist and realizes the importance of getting students engaged in physics education, but he's a fantastic researcher at the same time. There's many other types of active learning. Eric Mazur at Harvard teaches a project-based learning course, which is just project-oriented. So they might, they build musical instruments, and they study the physics of the musical instrument. The team has to design a space trip to Mars, so they study the principles of mechanics, Kepler orbits, chemistry, interactive learning, and these projects last 3 months. So project-based learning is another big part of active learning. I'll just focus on these things because these are the things that we do, but there's many, many other types. It's by no means restricted to this, and I'll try to give a little bit of the spirit of it. Now, just to introduce the pedagogy, let me talk a little bit about physics for a second, so you can see what that I want to do today. When you teach mechanics, there's really 5 basic principles for first year physics. Newton's laws of motion, the energy principle. People call the energy principle conservation of energy, but that's misleading because energy is always conserved. It's a fundamental axiom of physics. How you use the energy principle in a variety of different settings is a little more complicated. The momentum principle, I call these other 2 topics, the torque law and angular momentum, those are more advanced topics. They're taught, it's very important for us, but I today just want to focus on those 3 first ones as examples of how do you teach these traditionally difficult topics, very, very abstract. How do you make them concrete? How do you make them interesting to the students? Now, again, just as a quick, one of the things, so I'll do a little physics first. Actually, we'll do a lot of physics today, I can't imagine that. So we'll start, when you talk about interactions in physics, gravitation, you have elastic interactions, spring interactions, you have contact forces, you're rubbing, we're standing, objects are floating, we're moving in a medium, so we have viscous forces. These are the basic core subjects of mechanics. If you're teaching electromagnetism, we have electric and magnetic interactions. And these are all very abstract ideas. And so what we want to do is teach the students how to identify them in the world and use them and see that they're all around them all the time. This is the physics that's everywhere around us. Now, again, pedagogically, the setting that we use, and I just want to introduce this, is we talk about, when you talk about any physical setting, you have to talk about what is your system. Is it a person? Is it an object? Are there 2 objects? The concept of system is absolutely essential. What are the objects? How do you describe a system? Temperature, pressure, velocity, position, the location of objects. And what are the interactions inside the system? Is it gravitational? Is it elastic? Contact forces? And so we have this idea of a system. And for instance, if this room is our system today, system consisting of people interacting, we have surroundings outside, and if the door opened, then there would be a flow between the system and the surroundings. And people can move out of the system or into the system. Energy can move out of the system or into the system, etc. And so the idea, system, surroundings, and then what governs the way the system evolves are the laws of physics. And those are essentially what we call the equations of motion. And they describe how a system at some time will evolve to a later state. It can be infinitesimally, or it could be describing the system now in this room. We would say, where are all the people? Where are they located? We could all move around, people could leave, come back, and we describe the system in the room. Half an hour later, different people, different positions, etc. So the laws of physics govern how systems evolve from one state to the next. And we have some big principles, energy, momentum, angular momentum, which help us describe how to describe the system and how it's changed. And those are the ideas that we try to express to our students over the course of the mechanics course. But at the same time, when we ask, how do systems change? We want our students to have some models for how those systems change. So often in high school, we begin with, in physics, with constant acceleration in one-dimensional motion. And this is something that can be handled mathematically. It's not that complicated. And so that's a model for motion. And we approximate lots of problems with that. And unfortunately, our students end up memorizing formulas and not thinking about what's really going on. But they just memorize a formula. And I don't know if you remember this one, but x equals 1/2 at squared is a classic one that students would use for the simplest model and extend it to everything. So when we talk about models of motion, we want our students to have a bigger picture. There's one-dimensional motion. There's two-dimensional motion without some central point. Just, I can take an object and put this up here and just throw it in the air. And that's two-dimensional motion. We can have circular motion, central force motion. Object can go in a perfect circle, or it can make some beautiful spiral patterns and not have any closed orbit. There's simple harmonic motion. Pendulums, which was the source of the clock. And in Italy, the technological history of Italy was based on the Benedictine model of Benedictine monks building clocks, and that's been a big part of Italian history. And then much more complicated three-dimensional motion. That's just objects moving. There's also rotational motion. Wheels spinning. This yo-yo is a nice example of a type of rotational motion. If I wind it up and let it spin. Yo-yos are fantastic examples of amazing physics. I mean, if you just let that spin, that's pretty complicated motion. And it's explainable, actually, from a good example of things that students can have fun with and play. Then there's gyroscopic motion and much more complicated motion. So going back, we have, let me just review this for a second. We have a way of this is the physicist's way of looking at the world. And at the same time, imagine a musician who's played their whole life. Their way of looking at the world is an understanding of music with hundreds and hundreds and thousands of pieces of music that they know, that they play, that they've lived with their whole life. And with having students learn about science in the introduction, these are sort of the pieces that students need to learn and become familiar with and play and just get to know. The same way a musician would know a piece of music. So what I want to now talk about, that's just a little introduction on some background for physics. Okay, then, so how do we go about doing this in our TEAL group? Now, the first decision in a classroom like this, I think for most teachers who are used to, presenting information, the biggest challenge in a TEAL classroom is how do you go from a model where you're always distributing information to focusing on whether students are learning the content. Now, we're conservative in what we do. We do a combination because our MIT faculty, they're used to lectures. And to radically change was difficult for many teachers. So it was a transition process. Whereas somebody like Eric Mazur at Harvard just completely rejects the lecture entirely and has moved to focusing on students working before classroom, bringing questions into the classroom, focusing on the fundamental ideas and seeing whether or not students actually learn that. So there's an alternative, there's a whole range that teachers can adapt. And there's no one way to do this. So in our class, we do mini presentations. So for instance, as an example, if you wanted to talk about Newton's second law, I would spend in the TEAL classroom maybe 10 minutes talking about the second law, introducing it, and the idea, there's a number of different versions. In the Principia, what Newton talked about was that if you take an object and you apply a force, you're going to change its momentum. But he didn't really call it a force, he called it an impulse. So if an object were moving and you hit it, you would be impulsing the object, and that would cause its inertia to change. So Newton, in the Principia, Newton described it as impulse causes momentum to change. Physicists call impulse the force times the time that you're applying the force. And then after Newton, this idea of over finite times became instantaneous with Euler. And that's where the differential version came in. That instantaneously, if you apply a force, you're instantaneously changing the momentum of an object. And then finally, you can, if the mass of the object doesn't change while I'm applying the force, I apply a force and the mass doesn't change, so I can refer to the same idea as F equals ma. Force is proportional to the acceleration of the object. Now, this is extremely abstract. And how do we bring that out to the students? So I want to show you a little bit about why this is abstract. If I asked you this, let me ask you a question now, okay? So we'll have a little discussion. If I said 5 are, so the way we'll do this discussion is this. So I look at a room, and the first thing I see is how are the tables set up? Because different classrooms can be set up different ways. For instance, you could make a choice here and have, here we have a hexagon, 2, 4, yeah. But you could also have 3 tables and 3 tables. So instead of having 3, 6, 12 people, you could have 2 tables of 6. And each table, when I look at it, has a possible group. So what I'd like the tables to do for this discussion is form groups of, say, 3 or 4. And I look around, and I would say, and I'll just, facilitate this by saying, if you 3 can form a group, if you 3 can form a group, if you 4 will form a group. So we'll say, if you 3 would form a group, if you 3 would form a group. Actually, I think this one. If you 4 would form a group, if you 3 would form a group, and if you 4 would form a group. Okay, so those are our groups for what we do today. All right, so, and then when we have discussions, so first thing is, you probably know each other, but just take a minute to introduce yourselves to each other, just your names and who you are, because if you want groups, people need to be relaxed, especially the students, they need to know who each other are. So just, let's take a minute and just introduce yourselves to each other. Okay, so, it's always... okay. Oh, he had to do teeth. Okay, so this is always interesting because people can exchange so much information in just a short time. I mean, just imagine all the things you found out of each other in just 1 minute. And that was just not there when you were sitting listening to me. Now, when we do group activities, we're all, you know as a teacher, if you ask students to, suggest stuff, you get dead silence sometimes. So when there's a group, one of the first things we'll do is, and this can rotate, but we'll appoint one person in the group to be the speaker for the group. So just choose one person in the group who, when I call on the group, will then be responsible. Imagine our students, and they have to speak. Imagine the same issue for students. They're trying to talk about the science, and they feel the same way about talking in English that we might. Now, or me in Italian, which I wouldn't even do. So one has to respect the fact of all that uncertainty and fear publicly. So one of the goals with the group discussion is that now, you can, first off, you can alternate between people. So, during the course of classes, not the same person is always talking. And this gives everybody an opportunity to voice, which is a challenge for students who don't normally talk in class. But at the same time, the goal is always, and I'll talk a little bit this morning, when we do group activities, we never grade them on right or wrong, we grade them on effort. But the idea is that the group works together, so who's ever speaking doesn't want to be embarrassed. So the group has a responsibility to help the person who's speaking come up with whatever answers there are. And so I think that's a way of getting the students to learn to work together, cooperatively, and it's really, I would even say non-competitive. The goal is for the team to come up with an answer. Oh, yeah, okay, yeah, please. Yeah, so, by the way, at any time, if I say something, please interrupt me, and let's do this. Okay, okay, go ahead.
Prima diceva che è importante il compito dell'insegnante perché dividendo la classe in gruppi si deve dare un ruolo di speaker a uno del gruppo, che però non necessariamente deve essere sempre uno, ma si possono alternare. E poi l'obiettivo non è di valutare lo speaker, ma è che tutto il gruppo deve lavorare in cooperazione per aiutare colui che deve esprimere le idee, e quindi non per raggiungere un voto, una valutazione, ma perché il gruppo deve collaborare per raggiungere l'obiettivo.
Thank you.
Grazie. So, I'll give you one special question now, because it seems so simple, but it's actually will illustrate this physics principle. If I told you the following thing: 5 apples equals 5 oranges. 5 apples equals 5 oranges. What does the equal sign mean? That's the good question. Well, discuss. Yeah, just discuss. You got your students. I mean, I expect you to know the answer. This is... their class. So it's important to see and hear this. When you start a discussion question, the number one issue is, as a teacher, you're letting go. Right? You know, we control our classrooms very carefully, and if we say the students can now talk, then they're going to talk, and not always about the question. They may talk about other things. And so one has to have an agreement with the class that when you have a discussion question, and it's over, how you come back together as a classroom. And this has to be discussed with the students beforehand, or else it's always chaos. So for me, I'll just say, please, let's reconvene. That way, But because everybody is incredibly cooperative, it works. Doesn't always mean it works in the class. So you need to figure out, if you're going to have some type of engaged activity, how do you bring the students back together? And there has to be an agreement with the students about this. And they have to be part of this process. It's an important thing. This isn't just imposing, but it's the whole class and the teachers working together, which is a different model for pedagogy. Again, when we started this at MIT, our students didn't really like it because they weren't used to doing any group work, but that was in 2001. And since then, social media has totally transformed how students interact. And going from a period when they just were very private learners to now much more social learners. This is a big, big change. And anyway, so let me just ask, what I'll do is I'll ask a couple of, this question's easy. I'll just ask someone to say from this group, who's the person, what was your response? You can say it in Italian.
Allora, sono sferiche, hanno la gamma del giallo e dell'arancio come nome, rotolano, cadono dall'alto. Allora, sono frutti. La stessa forma sferica.
It's important for everybody to listen because I'll ask another group to listen to what this group is saying and add something that maybe they didn't say. Okay, so go on.
È lo stesso colore della gamma del giallo e dell'arancio. Rotolano. Cadono dall'albero. Sono commestibili. Contengono le vitamine. Hanno un picciolo. Poi sono nella stessa quantità, 5-5. Hanno la buccia e poi sono dello stesso ordine di grandezza.
Okay, that's great. Thank you. So they said a tremendous number of things. And in the course of what they said, there's a lot of pieces that can be pulled out of it. I'm going to ask another group if, from what they said, what would you say, how would your reaction be to all the things they said? So, who's the speaker in this group?
We understand differently the question. We try to answer, no, stai qui Federica per carità. So we understood what
okay. Because I couldn't sort of understand.
Okay, thank you. Noi abbiamo interpretato in un altro modo la domanda e ci siamo chiesti che senso ha il simbolo uguale. Non di trovare le similitudini tra i due insiemi, insomma, ma perché c'è il simbolo di uguale in mezzo. E quindi abbiamo dato una risposta così praticamente. Uguale significa che sono due insiemi con lo stesso numero equipotenti, insomma, con lo stesso numero di elementi. Ecco, questo abbiamo risposto.
Okay. So two different approaches. One describing the properties of the objects and the similarities between them. And they told me they were mathematicians. So I knew that. And the important thing here is that, Wrong one. I'm sorry. I hope I didn't mess that. This one's okay? Okay. So, over here, apples, and over here, oranges. And if I put an equal sign in, where we have 5 and 5, the equality is in number. It's a scalar. And it's not, oranges and apples aren't different, there's a lot of similarity, but they're really different things. So when we talk about equality between two different things, the first way we talk about it is in terms of number. There's 5 oranges and 5 apples. And that's what the equal sign is. Now if you think about it, it seems such a simple thing, the word equal in English. What does it mean? So now let's look at physics. So instead of an eraser for this board, an eraser can I use? Can I use this one? Okay. So instead of saying, if I talk about force, and I write it with that symbol, and I talk about mass and acceleration, and I use a symbol like this. Now this is a harder question. Now, what does the equal sign mean here? So now let's have a discussion again. What does the equal sign mean in this equation? So Newton's second law is at the heart of all of physics, and it's an extremely complicated principle. And here we're just dealing with an equal sign, you know. But it's important. So let's try a different group. Can I get your group to just comment?
Allora, noi abbiamo pensato a un concetto di uguaglianza paradossale, nel senso che faccio riferimento alla differenza tra senso e denotazione. Se io parlo di forza e parlo di massa per accelerazione,
Io solo paradossalmente mi trovo di fronte alla stessa cosa. In ambito fisico qui si potrebbero includere per esempio gli attriti che sfuggono ad una prima eguaglianza a livello di nomenclatura. Quindi è il paradosso dell'eguaglianza, perché per quanto può essere simile non è identico.
Okay, so the paradoxical nature here is that there seem to be different things. Now, let me explain how different they are. Mass is a property of objects. A property of objects. When we talk about mass, there's subtleties with the concept of mass. E equals mc squared, gravitational mass, inertia mass. What do you mean by the mass of a massless particle, like a photon energy? So it's a very complicated idea, but from the simplest perspective, it's a property of objects. We know how many kilos we weigh. Acceleration is a mathematical description of motion. Technically, it's the derivative of velocity, and velocity is the derivative of position. So it's a pure description. The way Galileo said that the mathematics is the natural language to describe the world. So acceleration is just a description of motion. If I take this object and I say it has a position, it's at rest, no velocity, no acceleration. If I move that object, it started with a velocity, it slowed down, so it had an acceleration. Just a description of the motion. You can use mathematical language, mathematical symbols to do that, and that's what we teach our students how to do in their math classes. Force is something completely different. It's a kind of induction process where you look at the world through measurement, deduce, and this is where the physics come in, what are called force laws. How do two objects interact gravitationally? If you have a spring, and you pull the spring, what is the force of interaction between the objects and the spring? If you have electrical charges near each other, what is the force of interaction between those electrical charges? While this yo-yo is sliding, there's friction on the surface. How do we describe the friction force? So these forces, viscous, all the interactions, those are properties of the world that we need to experiment to make models for. Sometimes we can express those interactions mathematically, and sometimes we can't. There isn't a mathematical law, but sometimes there is. Because we have our models. As an object falls in the air, depending on its speed, the air friction will depend on how fast it's going. And there's some other properties of the object. So we build models, and on the force side of this equality, that's where we observe nature. And we have these laws. We talk about what is the force of gravity on this object. People in English call it the weight. I'm not sure what it's called in Italian. But that force, we have a law, and that's what Galileo found. He found that the law is that the force is proportional to how much mass there is there, and there's this gravitational field, G. So the force would be different on the moon, or Mars, or on the Earth. It depends on the gravitational interaction between the Earth and the Sun. So what we have on this equality are two very different things. The right side, you can call it mathematics. The mass is a little bit different, the property of objects, but that's a mathematical description. The left-hand side is physics. So what we're doing is we have oranges and apples. They're two very, very different things. Now the question is, what is equality? And the equality here is more complicated. There is an equality in number, in magnitude. The magnitude of the force is equal in number to the magnitude of the mass times the magnitude, The mass times the magnitude of the acceleration. But these funny symbols with arrows above them, those are called vectors. And vectors have direction. So this is an equality in both magnitude and direction. If you apply a force, there's two different forces. While this object is sliding, there's friction force opposing the motion. So the friction force points this way. And if I measure the mass of that object, and I measure the acceleration of the object, and by the way, in your classrooms, if they all have iPads, there's a lot of applets that you can get on the iPads that will actually take video and measure the acceleration. So you can use the applet on an iPad to measure the acceleration of the object. It's cheap, it's easy, and they can be downloaded. I'm sure in Italian one can find them. So all types of ways of measuring things are showing up on the desktop computers. So they could actually take their camera as an exercise, just do that, and make a video, and measure the acceleration. They can put the yo-yo on a scale and measure the mass. And so now the right-hand side, MA, is known. It will have a number. And if you ask what was the friction force on the object, it would have the same magnitude, units, newtons. But here's the important thing, is when an object slows down, because its velocity is slowing down, the acceleration is going the other way. So it's braking. So the acceleration pointed that way, and the friction force pointed that way. So if I made a picture of this, I might do something like this. Here's my object, and let's start, well, it's a yo-yo. And it was moving with a velocity. Maybe it started here, it ended here. So in the course of that motion, it was accelerating the other way. So this is what we can call an acceleration diagram. And the important thing to realize is there's an arrow. And over here, we can make a separate diagram. And what are the forces on that object? There was friction. The earth was attracted with downwards. The ground is pushing the yo-yo upwards. These forces balance, and this is what we call a force diagram. Now, the equality is that this arrow is equal to this arrow, MA. What equality means is the length of these arrows are the same and the directions are the same. And so we have force as a vector quantity is equal to this description as a vector quantity. These arrows, so what we're doing is we're representing this abstract concept with pictures. Acceleration diagram, force diagram, arrow, arrow. And the idea is the arrows have to be the same. And that's Newton's second law. Mathematically, I can say the friction force equals MA. Mathematical representation of it. If I know MA, if I know this side by using the iPad to take a picture, a scale to measure N, I can predict this side. Sometimes we know the force from first principles, and so we can predict this side. And that's how physics works. So here, what I want you to do is take a very complicated concept like Newton's second law and show how through discussion we can get at the fact that most people, you know, it's difficult. Many people have never thought about it. You told me, honestly. I have no idea what the equal sign means. By discussion questions, you alert students to where the issues are. And then we come, so that's the practice. People say all types of things. And people comment on each other's. And then we get to the main point. Now, this is such a misunderstood idea that if you rush through Newton's second law, which is at the foundation of all of science, and students don't understand it, which most people will remember their experience in physics, is that they didn't understand this. And then they got scared, fear, all that stuff comes in. And so there's no learning. So a whole point that Eric Mazur makes is that one needs to focus on the learning. And this is tricky because you have curriculums, you have national, all types of stuff that you're forced to do. At MIT, we have much more flexibility. So we make a decision, we're not going to teach as many topics, we're going to go into each topic in more depth until the students learn. So we always want, we don't want to cover material. Whatever we do, we want to make sure that they learn. And I think in the long run, when they need, if they understand Newton's second law, and they need to apply it somewhere else, they have a much better chance. If they just memorized something, forgot it, were confused, never understood it, and then went to another topic.
I think the case that Federica translates, this last concept. Thank you. It's very important.
Sono completamente d'accordo, adesso traduco. Sì, in effetti diceva che questi concetti astratti, se vengono memorizzati semplicemente, poi si dimenticano. Al contrario, se questi concetti vengono concretizzati e ci sono esempi in ogni momento e tutti i giorni, questi ragazzi ovviamente apprendono, e prima di passare all'argomento successivo bisogna essere sicuri che i ragazzi l'abbiano capito, e inoltre se questo l'insegnante capisce che non è stato raggiunto come obiettivo, si riprende e si ripropone in modo diverso. E quindi adesso questo aggiungo io, di non essere costretto al famoso programma, ma in realtà esatto, e quindi diceva, cioè, di passare all'argomento successivo nel momento in cui abbiamo capito che i ragazzi dall'astratto al concreto hanno capito bene, quindi si può procedere. I said that I completely agree with you because yes, everybody was, because in Italy we are very strict because we think that the program that we should do every year must be done at, from the beginning to the end. Instead, we said that one topic and completed that, and later on we have to go on, but before we must be sure that our students have already understood and well.
And also, if I say, we have too much subjects in our schools. It's a sort of bulimic school.
Well, this is the challenge with teaching. I mean, every teacher faces that at every level. I think it's harder at the high school level than it is at the university level, because we can make choices. And at the high school level, you're much more fixed on what you can and can't do. So, and one has to realize that in active learning, things take time. So this is, you know, a balance. I mean, we're spending, you know, so now again, I want to come back to what Eric says, is he just completely gets rid of the lecture side and focuses on just asking students a series of exercise questions and activities based around whether they're really learning this or applying. It's a challenge. I chose to do a mixed version of presentation and interaction, but for me, what I always think is important is, well, I'll get to this point in a moment. I'm actually going to talk about problem solving in the afternoon a little more. No, I'll get to that. So now I'm going to turn to something that's kind of fun and show you a little bit, is about concept questions. So again, this is something that Eric Mazur developed. And let me see if I can get my device over here. Okay, so now you all have these clickers at your table. Now, these devices, let's just make sure they work. So what you can do is, I have on my computer something that I can pick up the responses. So you can see I have a little polling closed this thing up here, and when I open it, it should now say polling opening. So now click your device. So does everybody? Let's make sure that it doesn't matter what you click. Just click one answer. So you see the responses are coming up. Does everybody have a click? Yeah, you have one. Does everybody have one? Here's another one. Oh, you passed one. Here's another one. Okay. Does everybody? Do you have one more quick? Here's another one. And you need, yeah, each person. Okay, so we should get, if everybody click now once. So we have 13 responses, but we have 4, 8, 11, 15, 18, 21. I should get it up to 21. Can everybody click their device once again? So it's in front of you. Just click it once, 15, 16, 17. But just click any answer. Let's see, 18. Okay, I think I have 6, 12, 11. No, somebody's not clicking. Everybody click once. Just click any. Click 1, 2, or 3. Click 1, 2, or 3. All right, well, it's maybe for some reason one is not working. I'm not sure why. 4, 8, 10, 21. You should have 21. Well, we got another one. Okay, anyway. You have to make sure everybody's working. Now, when I'm done taking answers, I get a bar graph like this. So I can see in real time what your responses are. But I don't show that to the students. That's just for me. I'm going to show it to you, but not to the students. Now, there's a lot of different technologies. You can put technology on the iPad that does this with the iPad itself. There's things called, I think, Clickers Anywhere. There's a variety of softwares where you can get these turnkey ones. Way too expensive. And I just use them because it's easy for me to move around. But having schools that, when Eric designed the system, Eric Mazur, he just had colored cards with numbers on them, 1, 2, 3, or 4, and students would put them at their foreheads. So the point is to have an opportunity to answer a question anonymously. Now let me talk about the methodology behind these clicker questions before I do one. Okay, so Eric calls this a concept test. Now, this is very important, the methodology. And for teachers, this part is always a little challenging. Students have more, it's easier for students to do this than teachers. So let me explain what happens. I'll pose a concept question, which gets at the core concept of a major issue. The point here is that I want everybody to think individually first. And this is a commitment on the part of the teachers. It doesn't matter whether you get it right or wrong. And this is the challenge, because a lot of people are often afraid that they might get a question wrong. But everybody needs to commit to an answer. And that's what practice is all about. If you kick a ball or play an instrument, you're playing a note, it's either right or wrong. And it's important to know whether it's right or wrong. Because I think the first part of when you focus on learning, and we always tell our MIT students this, is that it's most important thing is to know what it is you don't know. To identify that, to crystallize that, so that you can focus on that. And learning is just going through what I don't know, what I don't know, what I don't know, what I don't know. And that's an ongoing process that never ends. And if somebody is lucky and does that their life, we call them a lifelong learner. Many people truncate that process. Unfortunately, they truncate it too early. But if you can keep that process going your whole life, then we call that a lifelong learner. So the first part of the concept question is to think and come up with an individual answer. It doesn't matter whether it's right or wrong. Then, this is the fun part. Two things happen. As a teacher, I can see what everybody's responses are. So right away, I can judge whether the class, anonymously, understood a concept. Chances are, and this is really surprising, most good concept questions, only 40 or 50% of the people get it right the first time, after a presentation. Now think about what that means. You present something, and we do know how to present things. We make a good explanation, and yet only half the students generally get it the first time. That means half of them don't. And that process just continues until cognitive dissonance sets in. You know, they feel so confused. You know, 50% the first time, 50% the second time, 50% the third time, and then you're down. You know, that's why, you know, science is often gatekeeping, because this process goes on. So we can see the response. And also, when the students discover that half of their peers don't understand it, didn't get the right answer, then it's much easier to talk about things. Because many students feel, and at MIT, students tell me this all the time, they feel like they're the only one who doesn't understand it. And they suddenly discover that everybody really is having the same difficulties, and that's a liberating concept. Because it's no longer just me, but we're in this together. So, but as a teacher, I get impact immediately, and I can make a judgment, how much time do I want to spend on this concept? And that, so Eric will just choose 8 of these questions and teach his class going through these questions, spending as much time as he needs on each one, seeing what the response is. Now, so then you think individually. And I really want, people will have to be quiet during this time. We'll take about half a minute. Again, it's not so crucial whether it's right or wrong, just an answer is important. And if you don't know the answer, just, you know, sometimes people put on one of the questions, I'm not sure what the answer is. Okay, then the fun part comes up, is that the group discusses the question with each other. And what happens is, it may be that the whole group will say, well, none of us understand it. But also, this is where students can help each other. They can teach each other, those students who, and they learn to discuss and express ideas. And they have a chance of doing what's called peer discussion, peer instruction. And then the whole group can revise their answer. And you can either take them individually again, or you can ask the group, I just want the group to come up with one answer. So make sure you get it right. You know, so you put a little more pressure on the group. But a lot of different ways of doing it. Normally what happens is the number of right answers goes up from maybe 50% the first time to 70, 80, 90%. It doesn't mean that students have learned this concept. It just means at that moment, a lot of students now understand what the right answer is. Learning is much more complicated. This is, we're talking short term in the classroom. And if you sustain this over time, then we can maybe talk about long-term retention. But we're just talking about while the topic is being discussed in the class. Now what's interesting is the explanation to the question. Because now that the students have got it right or wrong, talked with each other, now they're ready to hear an explanation. Because they've practiced, they've made mistakes. And that's the beauty of this, it's very elegant, simple idea. People do it all over universities and all different disciplines, and it works. Explanation, you can do it a lot of different ways. The group, I can call on one group to make an explanation. I often say to my students, would you like to hear my explanation now? After they've gone through that process. So there's many ways, I call it closure at the end. Many ways to accomplish closure, not just one. So let's do it. Here's a group question. Oh yeah, go ahead.
I try in English, but I'm not sure you understand. For example, which kind of question you could do?
Like this?
Yeah.
Okay.
The question you did before, or a question more light?
It can be any type of question. It can be a language question about, here's, you're working in the past imperfect tense in French, and here's different verb forms. Which one do you think is which expression is the right expression? And decide. So the idea behind these questions are to put the core idea.
Yeah, this is a core idea.
And design a question around what you think. And this is where the expertise of the teacher comes in. Is that, and this is where, now there's a lot of questions online already. Well, the FETs in learning, in their lesson plans for sciences have a lot of online questions. I think this is something that one builds up over time as a teacher, where you use your expertise to identify what is, and so I would just recommend maybe do 1 or 2 per class, or just even 1 per class. See if it works. Maybe you need to write a different question. And so over time, you see what type of question works really well. And then you can keep those and share them with your colleagues. Because these questions are not become a kind of content that you can share with your peers and say, I taught this course, and so a TEAL classroom can build a library of questions that works for the students at that level. And one can go online and find questions too. We share all of our questions in mechanics and physics. So with Christina, I can set up a Dropbox and put our questions in there. I'm happy to share. By the way, all our materials in MIT we share.
Sorry, and the first step is to underline or to the misconception.
Well, so the way Eric developed this was that he would first give an exam question, like what we call a blue book question, and students would have to write responses. And he would look at the responses, and he had his education team do this. They would choose 5 of the most common responses, 4 of which were wrong and 1 was right. And so that's where they would put the misconceptions. And they would build a question. So that's a very nice, simple way to build these questions. So let me give you a question. So here's one for us. Okay. So we're going to do one. Now remember, I want you to do this on your own first. So if you're not a physicist, don't worry. But I want everybody to respond on their own. So the question is, a person is standing in an elevator that is accelerating upwards. The magnitude of the upward contact force on the person is greater than, equal to, less than the magnitude of the downward force, everybody quiet, on the person. So let me translate this question into Italian. Can you translate?
Allora,
ho guardato questo fenomeno di notte ieri sera. Allora, qua è considerare una persona che sta in un ascensore, che sta viaggiando verso alto, e magnitudine del contatto, della forza del contatto che va verso alto sulla persona e ti dà le 3 scelte, no, gli allievi, che è più D uguale A o meno D. E magnitudine della forza è il basso della gravità. L'intensità, ok, sì, avevo cercato dell'intensità della forza che tira il basso della gravità. Dunque di lavorare su questa seconda legge di Newton e far sì che gli allievi pensino e che si chiedono queste cose. Ok, sì, molto probabilmente no. Ok. Infatti io sono andata anche online a spostare dei discorsi di italiano.
Okay, now everybody take your clicker. This is important. Answer on your own. So now you've seen the question. Click on 1, 2, or 3. Wait, I have to get the polling is open. So let's click your answers in. And we can see the number of responses. We only have 2 responses. 3, 4. Click again. It will only take your last answer. Everybody on their own. It doesn't matter whether you get it right or wrong. No talking. Not yet. Not yet. Ask you.
Translation is supposed to translate.
Okay. We only have 6 responses. I should have 19. So, wait, can you answer again? I think we weren't getting responses. 7. You shouldn't have much more. It will always take your last response. 1, 2, and 3. Well, whichever one you want. 1, 2. It will take your last one. 1, 2, or 3. So I want everybody to click once again because we had 20 before. So click what you think. 1, 2, or 3. There we have 15. We still didn't get everybody. Did you all?
Chi non ha risposto?
Just click once again. Okay, everybody click. All right. I'm not sure why I'm not getting everybody to click, but that's okay. Now we stop it. Okay. So now talk with each other. Which answer is right? But when you talk with each other, try to think about what I said. And what I encourage students is take some, if you have paper by any chance, see if you can draw what you think the pictures are on both sides. So see if you can take some paper out. Do we have paper? Can we get some? Okay, we'll get. Okay, so let's talk about it with each other. Talk about it with each other. So every group, let's click the answers. So normally we'll allow, you can allow 2 to 3 minutes to listen to the discussion, but I think this is good. So everybody can hear answers again. Now we should get up to 19. So Now, we have only 15, we should have had more, but that's okay. So, a little bit. There are changes for teachers. Changes for students, but rarely changes for teachers. So, here's, okay, so let me ask one group to just, can I ask to say,
Chiedi al gruppo quello che comunque ha pensato e perché. So why did the answer number one?
Allora, rispetto a una situazione in cui l'ascensore è fermo e quindi noi rispetto all'ascensore siamo soggetti a una forza di gravità, la nostra forza di gravità, quindi sarebbe la risposta 2 in questo caso. Nel caso in cui l'ascensore subisce un'accelerazione invece verso l'alto, aumenta la forza che l'ascensore attraverso il suo piano dà ai nostri piedi, e per una sorta di equilibrio fra la nostra forza applicata al pavimento e la forza che il pavimento dà a noi, premiamo sull'ascensore, sul pavimento dell'ascensore più di quanto proveremo senza questa accelerazione.
Okay. So he explained that thinking about you didn't think about the elevator, which is of course not moving. Obviously you have second, which would be equal to. But the moment that the elevator begins moving, the force of the elevator that is moving, the bottom of the elevator that is moving up, with respect to the feet, which are still pulled by gravity down, the greater force is on the elevator that is moving up. Obviously, this is just movement.
That's the right answer. Now, the misconception here is that students symbolically will always say n equals mg. They'll memorize that formula, no matter what the circumstances are, apply that formula. And it's just only a very special case when I'm standing, like in this problem. For the yo-yo, the ground pushed the yo-yo up. Gravity was down. Was there any vertical arrow here for acceleration?
Chiedi il discorso, ovviamente non so se io
No.
qua, chiedi se c'era una freccia che va verso la posizione verticale.
In vectors, when two arrows are in opposite directions, they subtract. So there's no vertical arrow here. So the sum of these two vertical arrows has to be 0. Because they're in opposite directions, they subtract. So the arrows have to be the same length. So when an object is not accelerating upwards, the ground force upwards is equal to the gravitational force down. And for the problem that we just looked at, when I was looking at this group, they drew this picture right here. Here's the person is our system. So the first thing is to think about what is the system. The system is the person. Let's do the NA side. Person accelerating up. This is a description of the motion. If we made this arrow NA, that's multiplying the length of the acceleration. How big is it in number by the mass? Now, on the F side, the forces, the ground is pushing, in physics we give that N for normal, the normal force. The ground is pushing the person up, and the earth is interacting with the person downward, mg.
E qua parla comunque della terra che spinge in alto, perché noi ci appoggiamo sulla terra che spinge in alto, mentre la gravità che ci spinge in basso. E queste due forze che si incontrano.
Because the acceleration arrow is upwards, which arrow has to be bigger? This arrow has to be bigger than that arrow. So the normal force is exerting a bigger force than gravity because the net result is to accelerate the object upwards. And that's the equal sign in F equals ma. Equation-wise, if I call upwards plus, the normal force is upwards, the gravitational force is downward, that's the arrow subtracted. And this picture shows the acceleration force upwards, ma plus. So now I've translated the pictorial into the mathematical. And I have an equation for n equals gravity plus acceleration. If a is 0, n equals mg. And now, what if the elevator were accelerating downwards?
Okay, I'm going to try and translate some of this.
So let's say
Okay.
you translate this.
I see. Yeah, I'm going to try.
If the elevator is accelerating downwards, which of these arrows would be
Chiedi
bigger?
se l'ascensore va verso basso, quale, cioè, visto che in una condizione di salita comunque la freccia che deve essere più lunga o più grande è quello che va verso positivo, se noi andiamo verso basso, quale sarà la freccia più lunga, più importante?
So, if acceleration is downwards, which of these arrows is now bigger? So just discuss quickly in the group.
Allora, in condizione normale, la freccia più grande va verso alto, la forza maggiore poi va verso alto. Se io emetto l'ascensore che va verso il basso, qual è la freccia che sta più grande?
Okay, so okay, now one of the interesting things, let me get your attention. So a couple of interesting points. I started off with groups, but depending on how you organize the tables, quickly different groups can start talking to each other. You know, that's a decision teachers will make in the classroom. Because it may be that, 6 people will start talking together. Or in our TEAL classroom, when we have these concept questions, often everybody is talking with each other. Nothing wrong with that. So there's many, many types of conversations that can go on.
Questa è stata di spiegare la condizione di tavola, che ovviamente sono tavole, però spesso succede che i studenti iniziano a parlare tra di loro, ovviamente, e succede anche qualche volta che le persone parlano contemporaneamente, quindi non è sempre finché si tratta di risolvere il problema di questo problema.
Now, if I spoke Italian, I would sit at the table and listen to the conversations. Because that's what I'm going to do. This is not making out what people's misconceptions are. If I'm standing at the table asking people, it's another matter. But in my class, I sit at the table and just listen. Because now I can figure out what the misconceptions are. And I don't want to interfere because everybody will start talking to me. Just so they go away. Because I want to talk, I'm listening, and I'm learning what the misconceptions are. And that's how I can deal with consequences.
Cioè quello che lui dice è che ovviamente, se lui parlasse italiano, sarebbe in grado di capire anche la nostra discussione e osservarli. La cosa più importante di questo metodo è di ascoltare gli allievi che discutono fra di loro senza intervenire, a scopo di capire quali sono i malconcetti che magari hanno gli allievi verso il problema, senza chiedere direttamente
like, why is 3 wrong? Give me a reason why 3 is wrong. Not just, I don't want just 1, 2, or 3, but I want reasons for each of these answers. Now, coming to this question, this is an experience we have all the time. One of the reasons I chose the elevator is because this is something that we experience. We go in elevators up and down all the time. When you go in an elevator downwards, nobody changed the earth. So this arrow here, that's what Galileo discovered. And Newton, reinforced that with the concept of force. The gravity arrow never changes. It's the mass of the person times 9.8 meters per second squared down. This arrow doesn't change. But this normal force does change. That's the arrow that isn't depends. And that's why it's difficult for students to realize that the force of the ground upwards varies depending on how it's moving.
Però poi ovviamente la gravità è sempre costante, invece la forza della Terra può cambiare, e quello è un variabile.
So I will put a minus sign for the arrow down. And now I will have a minus sign for n, the constant gravity minus n. Now this is what you feel in an elevator. If the elevator, somebody cut the rope of the elevator, and the whole elevator would fall down, there would be no elevator. Because the elevators are separated. So you see, this simple elevator illustrates all that equals everything. It's an experience that students have in their life. So we're trying to connect what we do in the classroom to things that they can experience in the world. We can go from pictures, different types of representations, pictorial representation, language representation, Italian, English, pictures, symbols, mathematical expression. But now, when we finally get to the symbolic, it's not just symbols, each of these symbols means something. N is the magnitude of the number of the normal force up. Little n is the mass of the element. G is a number that's associated with the earth. N is the mass of the element. And this is the magnitude of the mathematical description of the acceleration element. And having the students in the verbal discussion of is the final part of the process to bring it back into natural language. And I think we can reinforce this whole process by language in the school. On stuff that's up in this whole in the entire school. So it's an opportunity at the end of this process to translate everything back and to put it back into natural language. So that's an example of just consequences around one activity.
Sì, ok, allora lui praticamente cerca di dare un esempio che ovviamente gli allievi hanno avuto allo sperimentato la sua vita. Tutti noi siamo stati in qualche punto una situazione, dunque per gli allievi può diventare un modo di discutere comunque quello che risulta sollettere un calcolo della fisica, può diventare materiale reale, esperienza che gli allievi possono comunque associare a questo problema. Così facendo si inizia a tradurre un linguaggio della matematica con un linguaggio vero sia in italiano che in inglese. E lui ovviamente va a fare questo programma, ovviamente che vedo, credo che stia parlando di qui, comunque di inserire la lingua inglese in un contesto italiano tramite esempi pratici.
And just do something like this. Just take an object and raise it. That's the elevator itself. They can take their iPads and measure weight and figure out what the feeling was in their hands when they raise this object. Because that's the normal force. Actually, weight is a misconception. N is what I'm feeling. If I took my hand away, there's no N, and that's what G. My hand is what's pushing it up. That's not the earth. Just my students invent a video, to shoot something and measure something, use their iPads and show it on the screens in the TEAL. So now you can use technology to measure progress that could be measured with a watch, but are much, much easier to do with some great movies and visual technologies that can measure the space process. Especially around easy to use. So that's my first example of, again, you know, using physics, but just to show discussions, constant questions, technology concepts, and how one builds what I call academic. So, by the way, I have a lot of this. And remember, Christine, give me an idea of I can go on forever. Yeah, so this is and then so group problem solving, we just begin to so here our students use the boards, and there's two boards on each side. There are whiteboards up on each side. And what happens in the classroom is when students are solving the problems on the board, our teaching team circulates and comments all the things.
Ovviamente parla dell'uso della tecnologia e anche delle lavagne dell'aula, e l'insegnante circa l'aula da infatti le do io, che la
So we talked a little bit about groups, why I think they're important. And what we've noticed at MIT is that over the course of time, if you just do a lot of group activities, students get used to it. And they are used, and that's the power of social media now, is they're used to have students interactive than maybe 10 or 15 years ago.
Lui parla dei vantaggi di lavorare in gruppo e dice che comunque con tutti i media sociali che abbiamo ad oggi gli allievi sono sempre più abituati ad utilizzare le tecnologie e di discutere anche fra di loro sulle soluzioni pratiche per i discorsi scolastici.
There's many reasons why groups work. It might do everything to groups. I joke with my IT students, the only thing they did on their own was to get into university. This is the irony of high school education. Life is always groups. Everything you practically do is with other people.
Lui spiega che tutti si fanno in gruppo, l'unica cosa che loro fanno singolarmente è di entrare all'università. Cioè, l'ironia della sorte è che se lavoro sempre in gruppo per tutta la carriera scolastica, poi quando ti tocca trovare l'università lo devi fare da solo. E poi una volta che ci entri si sente con gli altri.
There's no scientist or engineer hiding in their room. They're working in labs and working with people. Everything is done. Wow. I think the non-competitive, constructive environment is very important. I think this encourages this. We have a lot of data on this in our physics courses. MIT is now 50% men, 50% women.
Wow.
Yeah. And I think, but physics isn't. And there's a lot of reasons historically why, because there's not yet enough physics women faculty. And so the mentoring process takes time. But I think in the interaction, in the classroom, when people are talking and working on this is a chance, I think, it strongly encourages women in STEM, science, technology, engineering subjects, mathematics. It encourages peer instruction. When I say peer instruction, people teaching each other. At the end of our semester, now I don't know if you, I doubt you, whether you can do this in high school, but our students nominate their peers to be teachers the next year. So I have a team of, we have 700 students. I have a team of 38 undergraduates who are helping me teach in the classroom.
Ovviamente lui parla di creare un ambiente dove non c'è per risolvere i problemi, perché effettivamente gli scienziati che lavorano anche in laboratorio non lavorano da soli, lavorano sempre in mezzo di un gruppo. Poi lui ci ha fatto notare che la questione ha sentito, non so quanti di voi avete sentito, che adesso alla RED sono 50% femmine e 50% maschi. Quello che manca adesso nella didattica ovviamente sono le femmine che insegnano, perché ci vuole un processo di mentoring, di preparare le donne per istruire gli altri in questo momento. Lui comunque parla del fatto di incoraggiare gli allievi di insegnarsi fra di loro, di fare di tutto, comunque di fare la comunicazione fra allievi per creare l'istruzione. Tanto che fine anno gli allievi fra di loro nominano una persona che dovrebbe essere l'assistente del professore prima della laurea, cioè undergraduate vuol dire prima della laurea, che aiutano gli altri allievi ad imparare. E lui adesso di 700 allievi ne ha 38 allievi che sono tutor agli altri, che aiutano i loro compagni ad imparare.
The student tutors are paid.
Yeah, we actually pay and job, and in transforming the culture, we wanted to make this position a prestigious position, so that students looked up to it.
Credits from it.
Excuse me?
Yes, about credits.
They could get credit. Also, we could give them credit instead of pay. We could get a teaching credit, and in fact, it should be a part of the experience of teaching and learning is that all students should have an opportunity to teach and should get credit for that.
Sì, lui ovviamente, cioè, la Cristina ha chiesto una domanda fondamentale, ma sono pagati questi allievi che comunque si prestano ore della loro settimana per insegnare agli altri, lui dice sì, è un tipo di lavoro, magari saranno un po' di corsi di studio, comunque ricevono qualche economico, e l'idea è di rendere questo posto dello studente insegnante un posto prestigioso che vogliono fare tutti, tanto che tutti gli allievi a loro volta dovrebbero mettersi nei panni dell'insegnante per fare tutti e due lavori contemporaneamente.
Now, in one of our classes, in my class, I have 2 women undergraduate teachers, 2 men. In another class, there's just 5 women are the undergraduate teachers. So when MIT students come into the class and they look who are the undergraduate teachers, and the female students see 5 women teaching, this delivers a message. I think that it's the best message you can possibly deliver about encouraging students and learning in STEM subjects.
Infatti lui dice che in un gruppo ne ha 2 che sono maschi e 2 che sono femmine di questi assistenti. Nell'altro gruppo lui ha 5, tutti 5 sono femmine, e dice che per incoraggiare comunque il nostro equal opportunity, cioè l'uguaglianza in questo campo, bravi sessi, che comunque è una cosa che fa un impatto, è più importante di tutta la politica che noi possiamo mettere in atto, c'è proprio l'esperienza, sia visivo comunque l'esperienza con questi insegnanti, vice insegnanti, quello che si può chiamare assistenti insegnanti, che sono donne, per anche le altre donne studentesse che arrivano al mezzo.
Okay, so again, well, now here's the interesting thing: is we have 700 students in the subject, 700. But the TEAL classroom, we have 8 different sections. So now we take our 6 to 700, and it becomes between 80 and 100.
In ogni classe c'è tra 8 e 100, queste classi sono divise le classi TEAL, i 700 allievi sono divise in 8 parti, quindi diventano tra 80 e 100 allievi per ogni gruppo.
I'll talk about this a little bit more in the afternoon, but we have tables of 9. So now instead of 100 students, I have 9 students. The tables are groups of 3. So I go from 100 to 9 to 3, and I can sit and talk with a person, and now it's one-on-one. So you can operate at many different levels in your classroom. I can talk to 100, I can talk to 9, I can talk to 3, I can talk to 1, I can talk to 18. So it depends on what the activity is. So there's many different levels of interacting that are going on in the classroom. So again, I just want people to think about the piano lesson, because for me, it's a really, any music lesson is kind of ideal one-on-one. Student practices, the teacher listens, gives them just the right exercise to practice, the student practices it, and then the teacher discusses it with the students. You probably know we have vocal lessons. And it's you know, it's a classic, it was the way education worked.
Allora, lui invece utilizza come esempio per il persona a persona, cioè il one-on-one, cioè insegnante-allievo, l'esempio della lezione musicale, della lezione in questo caso di pianoforte, perché abbiamo l'allievo singolo che fa parlare con l'insegnante, che l'insegnante ascolta, dà qualche pezzo di consiglio, l'allievo va a casa a studiare, a lavorare la guida data dall'insegnante e poi torna per aver risolto il problema.
So I think in the TEAL classroom, you have an opportunity to go from 40 or wherever you're 30. What is a typical size classroom?
About 30.
About 30. And just make it more individualized by the group activities. It can't be a one-on-one lesson. The students are in a huge range, and we're always struggling with that range.
Cioè lui dice che quando si tratta di delle lezioni, come ci sono qua che hanno 25-30 allievi, come nei nostri corsi, comunque non si riesce a fare il one-on-one, cioè direttamente con l'allievo, però dividendo i gruppi di questo modo e ascoltando comunque le risposte di gruppo e anche qualche volta qualche risposta individuale, si riesce a arrivare a tutti i diversi livelli, perché ovviamente il problema è la non omogeneità del gruppo e di rendere il gruppo sempre più omogeneo.
Okay, so the next 3 slides, I just want to summarize. I don't want to spend a lot of time on it.
Okay.
And the first one, we want our students to be expert problem solvers. It gives them confidence.
Se lui vuole solo riassumere questi 3 slide, come abbiamo detto prima, poi saranno disponibili per tutti voi perché lui mi manderà il PDF di nuovo aggiornato, quindi non è un problema. Comunque lui dice che qua vogliono creare gli allievi che diventano esperti di risolvere i problemi. E questi sono i modi e i motivi di fare.
By the time our MIT students finish, they solve about 10,000 problems as undergraduates. And this is the key, that they're just solving problems. So when they go into other environments, graduate school or the workplace, they're known as problem solvers. And they enjoy it. That's what they like to do. Now, the trouble is the beginning problems is what a lot of education does. And these are the typical things of difficulty in representing concepts. Unable to combine multiple ideas. Unable to apply mathematical reasoning. Symbol manipulation. Not knowing what the symbols mean, just manipulating. Not having models behind. Unable to estimate and make back-of-the-envelope calculations. That's what the expression we use in English. There's another expression for this. You may know it. They're called Fermi problems. Have you heard this? No. Fermi. It's named after Enrico Fermi. Everybody.
Cioè lui parla qua comunque di principianti, che ovviamente prima parlavamo degli esperti, adesso parliamo di principianti. Cosa si fa? Un allievo al primo anno che non sa come risolvere il problema in questo modo e loro l'incapacità comunque di rappresentare i concetti, l'incapacità di combinare diversi concetti, l'incapacità di ragionare e di applicare il ragionamento matematico, quello di impegnarsi con la manipolazione di simboli e poi di stimare e di creare, di fare e calcolare il back di envelope, cioè i problemi fermi come...
So if you hear an American say Fermi,
No, we say Fermi.
if you hear an American say Fermi, they're trying to say Fermi. And they're named after that. And I'll give you an example of that. So we want our students, we want them to start to think. And, you know, we reason from first principles with this F equals MA, and then we got to the elevator question. It wasn't a question of just memorizing N is mg plus MA or mg minus MA. We had tools in which to think. And that takes longer, but I think that's the important thing.
Ovviamente lo scopo qua è sempre di far sì che gli allievi iniziano a pensare da soli, che loro ragionano magari su questi concetti come abbiamo detto su questo dall'ascensore, cioè invece di vedere e memorizzare N uguale mg ma di applicare un'idea, una visualizzazione di cosa siano questi concetti qua con rispetto dell'altro.
So in the TEAL classroom, in an active learning classroom, when you're doing problem solving, in this slide, I outline different stages of problem solving. And so when you do a problem in the classroom, you don't have to do all of these stages. Depending on what the problem is, you can ask students to just do one stage or another. For instance, getting started. When you were thinking about this problem, you can ask the students, how are you going to get started on this problem? That's the group activity. And you can say, okay, we've learned about what are called force diagrams, and we've learned about acceleration diagrams. Before you even try to answer the question, draw some diagrams, get started. And then you have something to think about. You can discuss in the second stage, plan the approach. How can you use these diagrams to help you plan the approach? So you could do this problem differently. You could say, okay, here's an acceleration diagram, here's a force diagram. I'll get you started. Now, I want everybody to work on a strategy to answer the question. What ideas are you going to use to solve this problem? Will you use energy? Will you use torque? Will you use Newton's second law? Make a strategy. Come up with a plan for how to approach this problem. So that could be, or the activity could be both of those. The point is that you don't have to do every single thing as a group problem solver. You can choose the one that's most relevant for your needs in the classroom at that time.
Ok, vi spiego, ovviamente questi sono diversi modi per creare queste situazioni nell'aula. Lui dice anzitutto che non bisogna necessariamente fare ciascuna di queste attività un'attività di gruppo, ma scegliere quello che è più adatto per creare questo modo di creative thinking, cioè pensiero creativo. Dunque dice getting started, qua è il modo di iniziare, cioè come si fa, si potrebbe dire agli allievi, ok, come affrontiamo questo problema? Non so, facciamo un disegnino, facciamo questo, poi lui dice, eventualmente passi, io ti aiuto con l'inizio e si passa al modo di approccio, il modo di affrontare il problema, di articolare una strategia che potrebbe avere diversi concetti, forse lasci agli allievi quel passo lì. Qualche altra volta potrebbe essere magari di portare avanti il progetto, di portare a termine il progetto. Cioè, non importa quale passaggio di questi qua venga utilizzato per creare questo modo di ragionamento creativo, però che in qualche modo si fa sì che gli allievi inizino a pensare, iniziano a ragionare da soli e fra di loro.
So, I carried out the plan. And that you might be interested in the technical thing. A language class, you might have them actually, the important thing now is to carry out some type of conversation or some conjugation or whatever. So carrying out the plan may be the source of the group activity. Finally, in physics, it's in all science, it's really important to think about what you've done. Many students have the attitude that the point of a problem is to get an answer because that's what the teacher wants, and that's the end of the day.
Allora, lui ovviamente vuole creare la riflessione su quello che l'allievo fatto, perché ovviamente ci troviamo davanti a allievi che pensano che il punto di un esercizio è arrivare alla risposta esatta, al numero esatto, al risultato finale che voleva l'insegnante. Invece quello che mi dice sia molto più importante in questo modo è di far sì che ogni allievo rifletta un po' su quello che ha fatto e perché, in modo di risolvere più problemi nel futuro correttamente, non necessariamente una risposta singola.
and then at the end, I could have just done the whole thing and said, how does this correspond to your experience? So in a discussion question, or in some review, how does this problem that we did actually correspond to the experience of going up and down in an elevator? Because in science, every single problem is a building block in your knowledge.
Cioè lui disse che alla fine si potrebbe anche fare tutto per l'allievo e semplicemente chiedere: ma come rispecchia questo la vostra esperienza? Cioè ha un senso logico quello che abbiamo appena detto? Come rispecchia la vostra esperienza con un ascensore? È vero questa teoria? Non è vero? E chiedere comunque agli allievi di contribuire in questo modo qua.
Again, in the music example, every area learned or every piece of music is one building block in this huge frame of knowledge.
Che lui parla di blocchi, no? Per costruire la conoscenza, che ogni cosa che si impara, soprattutto come dice nella scienza, ogni passo, ogni teoria, ogni formula, comunque è quello che è un blocco per creare il prossimo. È dunque molto importante che gli allievi iniziano a ragionare su perché una teoria funziona prima di affrontare il prossimo.
Now, I have 3 more fun exercises that I'm going to do. We're going slow, but it's okay. I'm not going to say you need to focus.
I went on YouTube to try to understand this.
So, I'm going to show you them quickly. And then, and I'll ask you to play with them a little bit. But I just want to show you these 3. So the first one.
Lui ha 3 esercizi in più, vi riso, che guardava l'una di ieri notte, dunque.
The first one is about these Fermi problems. And circular motion, do you do circular motion? Circular motion is an important concept. It's another model for motion. It's relevant all the time. Students should know that satellite motion is an example. GPS, that's all circular motion. And how do we explain that to students? Well, when you do circular motion, you need some type of coordinate system to express it. Now, I'm going to introduce a coordinate system here that's not crucial for high school. But what I want to get at is the acceleration diagram. Again, where did that eraser go? There it is. So,
adesso ci farà risolvere il problema sul mondo circolare.
Okay, I'm going to summarize this quickly. But if you have an object going in a circle, then just in terms of acceleration, and say the speed is uniform. That means the magnitude is going in a circle 40 kilometers per hour. Constant magnitude. What's tricky for students to understand is that you're always accelerating towards the center. So when you go in a circle, you're always accelerating. Now, according to Newton's law, there must be an inward force. The acceleration, because it's inward, in English, we use the word centripetal acceleration. Now, the magnitude, when physicists or mathematicians talk about a vector, an arrow, they put these absolute signs to discuss magnitude. And the magnitude of that, and one can work this out mathematically, I'm not going to do it now. But it comes out to be proportional to the velocity squared, the speed squared divided by the radius of the orbit. This is a well-known result. There must be a force inward. That's what we call a centripetal force. That's different, because remember, forces and acceleration are different things. This is centripetal acceleration. The force is something physical. Is it gravity? Is it electrical force? Is it springs? Or is it anything? What is that force? And we can use the same idea if an object is going in a circle, and we know this and we know that, then this is known.
Ok, I'm gonna try. Ok, perché vado tanto, perché qua ovviamente parla del problema del mondo circolare e dice quando comunque abbiamo un oggetto che gira con il modo circolare è tirato sempre verso il centro, ok? Questo comunque la forza che centripeta che fa sempre andare più veloce verso il centro, giusto? Ok, perfetto. Dunque lui...
L'altro si chiama Virgiscale, sì, sono anche è lo scalare quello tra italiano.
Ok, e lui dice che comunque la velocità sarà uniforme in pratica. Allora lui ci dà ovviamente la forma per abbreviare a capire questo numero che vediamo dopo. Sotto vediamo il raggio, giusto? Sotto vediamo il raggio, il vettore, la velocità quadrato e l'altro è il vettore, la A è il vettore.
Questa è il valore scalare dell'accelerazione.
Ok, grazie. E lui dice, se noi conosciamo la velocità, se noi conosciamo il raggio, allora alla fine deve essere già conosciuto, lui ha messo no, saputo, conosciuto, comunque il valore scalare.
Okay, so a lot of that is just a prelude. Pictorially, let me see if I'm in here again. Okay, so if it was a satellite, the force inward would be gravity. And you don't have to worry about the r hats or the equation here, it's just an example. But if it's a satellite going around the Earth, there's centripetal acceleration, and the centripetal force is the gravitational interaction between the Earth and the satellite. Now, for a therapy problem, it's really important. This idea of what v squared over r is can be complicated. How do we get our students to think about it? So, I came up with an example.
Ovviamente lui a questo punto dice ok, potrebbe essere qualsiasi problema, ma lui dice come si fa a fare sì, e gli allievi iniziano a pensare, iniziano a ragionare, iniziano a cercare il metodo per risolvere il problema senza dargli direttamente il valore.
Driver Italian or American?
Laszlo.
This is the driver. Cosa, come si chiama?
I just came across this in the New York Times. I had an article about racing cars. And I didn't know that was from
Yes.
Yeah, it's very good.
They do a drive-through of classic cars every year in honor of this event.
Yes.
Yeah, they do that. It's always classic cars. You see the whole movie center of
We have also a museum.
Yes.
So here's the question. He's going around in a turn. So I want this to do, this could be a group problem to board, but let's just estimate.
Ovviamente abbiamo una macchina che va in curva, no? Questo è abbastanza.
This is strictly estimation. What is the magnitude of the acceleration of that car? I don't give you any numbers. You have to come up with numbers and figure out how that compares to g, the Earth's acceleration. So here I'm giving you an equation. Now we would spend time with my students deriving this. But so, for the sake of brevity, let's just take this as a result. So I'm asking you to estimate based on your experience in the world. He's going around a turn. And so, I'm not giving you numbers, but you have to put in numbers yourself. And this is important for students, because if you want them to estimate something, to be knowledgeable about applying real problems in the world, if you spell everything out, you've done it for them. So, let's just discuss in the groups, what do you need to estimate, and then make the calculation.
Okay.
And the answer should be not, 3.4825. It could be 2, it could be 5, it could be 10, it could be 20, it could be 30. It's an estimation. It doesn't have to be two factors.
Sì, lui chiede di stimare, allora, con la vostra esperienza con le macchine, senza utilizzare, cioè di immaginare i numeri, perché lui non vi dà i numeri, di utilizzare comunque, noi abbiamo la formula qua, comunque di creare una stima di cosa potrebbe succedere a questa macchina. Ok? Dice, ovviamente non deve essere una risposta esatta, cioè uno vuole semplicemente farvi ragionare, come tutti gli allievi, farvi ragionare su questo problema in modo creativo, per immaginare come potrebbe funzionare veramente nella pratica, nell'esperienza, nel mondo reale.
There's a couple of clues in the picture which I hadn't noticed. You can see his hand. You can see him lean. And you can see the big smile on his face.